Hi everyone, how's it going? Welcome back. Hi Labrude and Herb and Mountain Ash is here too. Hi to people watching. Last week, pursuit problems is what people are talking about in chat, which reminds me to plug the YouTube channel that's linked to this Twitch channel. If you want to catch the VODs, then I'm putting them on my personal YouTube channel, which I seem to have nabbed to youtube.com/@JamesMunro. I can't remember when I did that, but I got my name on YouTube. Didn't quite get my name here, did I? Oh no, I did. I got my name everywhere. Not everywhere. Don't check everywhere. How are you doing? You all right, chat? Having a good weekend? Right. Plan is I'm doing a bit more number theory, but slowly, because I tried doing number theory and I think I was trying to go too fast. It was weird. I was trying to go through things too fast, and then I got really bogged down in one not particularly exciting proof, and then I gave up for a week. But I'm back. I've found a thing that I care about, and I'm trying out some different study techniques. Hi, Mary. Good. This was partly a mic check. I'm always terrified when I start streaming that I'll forget to unmute. I suppose I could mitigate that fear by looking at the icon that says whether I'm muted or not, but, you know, irrational fear is gonna be irrational, eh? Tour to Speed, hello Mountain Ash. Also, I felt like I needed to motivate things a bit more. So there's this is a bit grandiose, but the study skill that I want to try is a sort of big picture mapping thing. I found this really useful for the Quintic quest. When about 6 months ago on this channel we went through trying to learn all of Galois theory, or enough Galois theory to understand why Quintics don't have solutions. I found the map really useful, so I'm going to try and do a little bit of mapping for just one topic from the number theory notes. Happens to be a topic that I care about. Hey, a cool person. Yeah, but I'm going to make it chill. I've got a Desmos thing up. Shall I explain that one first? I think I'll explain that one first. Yeah, good. Oh, I see. So I've just realised because I play with the what command before live. That gives you a reminder of what we were doing. I only update the what command while we're about to go live, which maybe gives you a sneak preview of what I'm about to do, because I don't know. I don't know miles in advance. Right. Okay. Here's the thing I want to play with. There's this really old math question about x squared minus 2y squared equals 1. The question, the old math question, if you want to dig it out, works like this. There are some integer points on this curve, like 1, 0 is on this curve. But do you know what sort of curve this is, by the way? Probably, if you're doing A level or something, then you might have seen curves like this. It's got squares in it, but it's not a circle. Okay, so the math question says there's points on this like 1, 0, which you can guess from looking at it, and there's points on this like 99, 70, which you maybe can't guess. Up here, exactly. I have to zoom in a bit so you can see, but that is exactly 70 and exactly 99, and it lies exactly on the curve. If you check it, 9,801 minus 2 times 4,900 is exactly 1. So yeah, it works out. Yeah, it is a hyperbola. Hi, Threshay. There's people. The nice thing about this, though, is if you have a method for finding these, or if you know that these large numbers exist that satisfy this, then you get this way to approximate root 2, because the large number solutions to this, and kind of spoilers for the math question, but the large number solutions to this, if x and y are both huge, well, who cares about the difference between these things being 1? X squared is pretty much equal to 2y squared. So you get this kind of thing that 99 squared is roughly equal to 2 times 70 square. And those are almost exactly the same number, which means that if I do some division and square rooting, that 99 over 70 is pretty close to root 2. Like, these things are just extremely similar. So if we can find more of these, then we'd have more approximations to root 2. Hi, Neutrino. Oh, you got a little, what's this? Oh, because you gifted a sub. You have a little present next to you forever. That's good. Twitch, always really distracting with Twitch features. Okay, so the kind of punchline for the math question is in the macro question, there's this way to generate more solutions to these, so that we can find more and more solutions like that, and they get close to root 2. That's the kind of motivation, I guess. But something else I'm interested in is the way that if you change this number, then you get slightly different curves. So this one does go through an integer point because it goes through, not that one. What does this one go through? I guess 2, no, getting there. What do I want? 4 take away 2 is 2. So I should put in 2 and 1. Yes, this point here. I should maybe have just looked at the picture. It goes through this point. So that's still got some integer solutions on, which maybe we could do something clever to generate even more. I can see up there, is that 10, 7? Yeah, that looks like it's on the curve as well. Which means, oh gosh, 100 take away 2 times 98 squared. Oh yeah, I know this one. This is the approximation 100 squared? No, 10 squared. What am I doing? 2 times 7 squared. 98 and 100 are pretty close together. The approximation 10 over 7? Yeah, it's pretty close to root 2. Okay, good. So we can find other ones like that. But sometimes this doesn't work. If you put a 3 on this on the right hand side, I can't think of any points that goes through. It kind of misses a lot of integer points. Yeah, should we try and get Desmos to only show integer points? Yeah. Dup. Dup. Oh, can I get it to not do minor grid lines? Yes, there we go. Good suggestion. Okay, so now when we zoom, we can look at these integer points. Good suggestion, Herb, thank you. So that's going through some over here and here. Oh no, not there. There? No. Well, if I put 1 on the right hand side, it's quite hard to see these things. Okay. So it's not obvious why I'm changing this number. It might sometimes go through integer points and sometimes not. Can check any suggestions as can we make any hypothesis or guesses about, if I put sometimes if I put a number on this right hand side, it does go through some integer points. Sometimes it doesn't. Can you guess any classes where, or groups of numbers where, if I put that number on the right hand side, it either definitely will or definitely won't? Doesn't have to be correct, but what's this doing? Is this going to do any of these? Doesn't look likely. But then this one does, because this goes through 3, 1. LaRue's put a question in, is it to do with Bazoo's lemma? And that's a hard question, right? Something about modular arithmetic. Okay, so guessing some relevant number theory topics. Yeah, so I was aiming for, there are some numbers which, when I put them on the right hand side, they definitely work. Hi, Chris Borsch. Nice to see you. Welcome to chat. Like if I put a square number on the right hand side, it's definitely going to go through the point n0. Yeah, ooh, so square numbers are 0, 1, or 5 mod 8. That is interesting. That's so interesting that I'm going to switch to a blank bit of paper. Oh, I switch. Switch. No, didn't switch. Switch. Oh, it switched. So elegant. Totally practiced. Massive professionalism. Okay. So in chat, Akul says mod 8, and we're thinking about x squared minus 2y squared equals, well, what? And Akul says that the square numbers are 0, 1, or 5 mod 8. I think I can maybe... Isn't it? What? I don't think anything's close to 5 mod 8. Let me check. So mod 8, you've got numbers like this, 4, 5, 6, 7, and then 8 would be the same as 0 mod 8. When you square it, so 0 squared is 0, welcome to the stream. 1 squared is 1, 2 squared is 4, 3 squared is 9, but 9 is equivalent to 1 mod 8. It's 1 more than a multiple of 8. When we write mod, we sort of mean more than a multiple of in this context. 16 is a multiple of 8, which says no more than a multiple of 8. 25 is 1 more. Oh gosh, 36 is 4 more than a multiple of 8. Careful, it looks like a multiple of 8. 32 is a multiple of 8. 7 squared is 49, which is 1 more than a multiple of 8. Okay, so it's 0, 1, or 4. Yeah, okay. It was a typo. 0, 1, or 4. So, if you look at the possibilities then, this is 0 or 1 or 4 mod 8. And this thing is 0 or 1 or 4 mod 8. So combining this together, we can make this question mark, let's call this n. So n is, I need to do some subtraction here, don't I? I guess this y squared is 0, 1 or 4. So 2 times that. Oh, that's rather nice. So 2y squared is 0 or 2 or 8 mod 8. But 8 mod 8 is the same as 0. That actually simplifies things by doubling it. Okay, so I need to take 0, take away 0, or it could be 0, take away 2, or 1 take away 0, or 1 take away 2, or it could be 4 take away 0, or 4 take away 2, mod 8. Okay, which is, so 0 or 6, or 1, or 1, oh no, minus 1, 7, or 4, or 2, mod 8. Which is quite a few things. Not 1, 2, 4, 6, 7. But not 3 or 5 mod 8. That's better than nothing. That's a prediction that if I put, well no, it's a proof that if we put 3 or 5 on the right hand side, or anything that's 3 more or less than a multiple of 8, then that won't go through any integer points. It's pretty good, I like that. Let me flip that in again. So we'll put in 3, the prediction is for mod 8 reasons, that this just will never go through any integer points. Good, okay. It's a whole class of things like 83. Oh, it gets pretty close to that integer point, right? 10, 3, because no good reason. It's not that close to 10, 3. 100 squared, take away 2 times 9 is 82, not 83. Oh, okay, so some near misses. Good. Close watch, yeah, okay. Let's give it a go. Maybe I'll be able to help, or maybe chat will. We've got a few people in chat who might be able to help. The way this works is you've got to describe your problem really well. And we're not very good at maths. We're trying, but we're not very good. Okay, I'm going to keep doing my number theory while Krujmoj describes something. And this feels like a good time to shout out to Carl Drogo and Joe Goldberg, who followed midweek. I get most of my followers on Twitch, not while I'm live, but just midweek, which I find quite funny. But welcome to the show. Oh hey, Joe Goldberg's here. There we go. Got you. What timing on the shout out. Okay. Oh wait, there's a question in chat. The limit of x is x as x tends to 0. Oh, okay, 3. Maybe chat's going to help. E to the minus, maybe it's e to the minus 3 over x, like this. Over x squared, depends on the brackets. And they want to know what goes on when x is positive and very, very small. This is interesting because yeah, okay, like that. Hi VC Aura as well. People in chat. Hey. Oh, Joey Goldberg. Hi. I don't know. I don't know either. At the moment, chat is asking about this limit. So what's the behavior of this function when x is really close to 0? Which we can cheat a tiny bit. We can have a quick look in Desmos. Like this. And we're trying to learn some number theory. So they've got this weird graph and they would like to know what happens as this gets closer to 0. So spoilers, it's very, very close to 0. In fact, it's tiny. This function just, for positive x, this function is just rubbish. Yeah. So LaRue's put a reason in chat, which is to do with comparing the exponentials like this. So that the function is equal to that. And then what we should really look at is how fast this goes to, well, does this go to 0 or infinity or something? 3 over x goes to infinity. Much faster than x to the minus 2 goes to 0. Yeah, cool, right, okay. Let's drop that one. So for Krujboj in chat, the thing you need to look at or think about is exponentials, how fast they go to infinity. There's a fact exponentials beat polynomials, which you normally meet as like e to the u to the n. So you might want to do a little substitution to say, well, as x goes to 0, 3 over x goes to infinity. So let's give that a name, like u or something. Okay. Right. For the benefit of Joe Gelberg in chat, a couple of weeks ago, I started looking at some number theory notes, and I went through them way too quickly, and I'm trying to slow down, motivate things, and actually learn some number theory. So if it looks like none of this makes sense, then that's a universal experience. Doesn't make sense to me either. That's part of the joy of learning maths. Right, okay. We ready, chat? I think we're going to look at the staff, because we can say a little bit more than this. I think so. This topic's in my notes. Right, here we go. I want to show you what's going on. This thing with the squares in, called a quadratic form, and the course, or the lecture notes that I found are actually doing something more ambitious to talk about not just this one, but to talk about this one. C. Oh, come on. Y squared. I'm trying to put coefficients on it. Equals n. So with different values of different integer values of a, b, and c, and asking whether the resulting curve that you get, which could be like this or like this or like this for integer values of a, b, and c. Ooh, something interesting going on there. To ask whether this goes through any integer points, depending on what you set a, b, and c to, like which values of n actually work and give you integer solutions for x and y. So this is a little bit like solving a quadratic equation or something, but with the restriction that you're looking for whole numbers. Number theory is often a bit like that you're trying to solve equations that you know perfectly well how to solve over the reals, but with the added restriction that you're looking for whole numbers. This is fun. So these things are called quadratic forms. Do your little dance. Do your little dance. There we go. Do your little dance. Do your little dance. Oh, I can animate. There we go. Oh, that's not great animation because whole numbers. Squishy. Go, go, go. Little quadratic form. Wait. Can we make it? How do we make it more like energetic? Or okay. Stretch it a bit. Is that going to make it more? Ooh. On the Thursday Maths Club recently, we talked about conic sections, ellipses, and hyperbola. And this is where ellipses change into hyperbola. I think that's going on the board. You want to increase the speed. The limits of 10 and minus 10 here are a bit interesting. Maybe a bit more? Oh no, a bit less. Interesting. Oh, because this 10x squared is now the most important thing that's going on. Whereas if I made this smaller, whoomp, and make this smaller as well. Okay. Work it. Right. Good, okay. So some of those, along the way, that vast variety of things, some of those go through whole number points. and I want to, not entirely today, not entirely today, but over the course of getting there, to find out where. Oh, this one's great. 2, 2, 1, 4, and look, because it goes through this point here, and also this point over here, and then down here, and also over there. When y is 2, x could be 2 minus 2 or 0. Have multiple solutions. Quadratic, say. Is there something in that? No. Right, okay. Revision strategy, which is also a learning strategy, or just getting to grips with some material strategy. I've got the notes. There's about 10 pages in the notes in here. And instead of getting bogged down, I want to try and map out what we've actually got. So this is called binary quadratic forms because there's only 2 variables, x and y. We'll save 3D ellipsoids oscillating in 3D space. We'll save that for another day, I think, another lecture course. Okay, my plan here is there's about 10 pages of binary quadratic forms in these notes, and instead of working through it in order slowly, I'm going to do fast first. So I'm going to try and write down one thing from each page. I've got a little list here. I'm hoping this will turn into a kind of map or a kind of overview of what's going on. These are the page numbers down here. So, for example, at the start we learn a binary quadratic form. It looks like ax squared plus bxy plus cy squared. And that's all I'm going to write down for this page. And the idea being that I'm going to quickly go through and list what's in there to get an idea of what sort of content we learn in this section. And then as I'm reading it, I'll have more of an understanding of how it fits together. Learning theories, right? You'll notice I'm talking about the learning theory quite a lot because that's easier than actually doing the task. Right, let's go. Okay, so there's more stuff here. I've already got my note from here, binary quadratic form, which I think I wrote down correctly. A, B, and C are integers. I'll just remember that, I think. And these x and y. Here we go. Good, okay. Right, one thing from this page. Some notes here about there's some matrices in here because you can write these things using matrices. Just for the benefit of chat, because that's something I've seen before, so I skipped over it, but it might not be something that you've seen before, especially if you haven't seen matrices before. There's this way of doing matrix multiplication. So if I if you've never seen a matrix before, it's a way of storing numbers, and there's a way of multiplying a matrix with a vector, which has got some great geometrical significance. It means applying a transformation to vector space, which is not important right now, I think. The thing that you do is you read across the row of the thing on the left and down the columns of the thing on the right, and you multiply terms together and add them. Wow, that sounds impossible, doesn't it? But you go along like this. So that's top row with this vector, multiplying the terms together and adding them. Wow, it's amazing how much I've internalized that as a sort of normal thing to say or do. You get this combination. Oh my goodness, so for this component here, I've gone along the bottom row and down on this column again to get b over 2x and cy. So you sort of multiply the matching things, you zipper them together, multiply the matching things and add all the things together. If this matrix was wider and this vector was taller, I'd have more things to multiply together and then add. And if this was a matrix over here, if I had another column, then I'd do the same thing again for the next column. Looking, instead of the first column, I'd look at the second column. Some people write this out like this. So they've got kind of 2x1 grid. BC Aura, we do have a Discord. We have an unofficial Discord. Somebody in chat is going to type !Discord and it'll appear. Good. Anyway, point is we then hit it with another one on the left. If we hit that and subsequently, thank you Neutrino. If we hit that with this, then we get exactly this ax squared plus bxy because there's 2 half parts of it and a cy squared. Good. Anyway, that just means that instead of writing out the quadratic like this all the time, quadratic form like this all the time. There's some matrix stuff going on. Good. It's also teaching. It's a teaching stream as well. What do I want to write down from this page? I can see some unimodular substitutions. We say that things are equivalent if they're related by unimodular substitution. I'm going to write down equivalent. And I'll just have to learn what this means at some point, but equivalent if related by a unimodular substitution. And okay, at some point I've got to come back and slowly go through and learn what a unimodular substitution is. There's a definition here, so I'll be okay, and to work out why that's important and what that's got to do with SL2Z. But okay, I like the idea of things being equivalent. I don't think I've got the point of them being equivalent, but I'm going to move on. Possibly they take the... the point is, here it is. The point is that equivalent forms represent the same numbers. Okay, worth bearing in mind. So they can take the same values. That seems good. Sure. So if we've decided that this one can't write in things that are 3 or 5 mod 8, then fiddle around with it and you'll get something else. Okay. Discriminant is on this page as well, but that looks pretty nice because it's the discriminant of the quadratic b squared minus 4ac. I already know that thing from A level. Okay, this one's got y's in as well, but whatever. Okay, I'll just know that, I think. Something's being proved here. Doesn't look important to me right now. Oh, discriminant's the same. It's saying that discriminant's the same. Is this what I write down from this page? It's level 30 here. Discriminant must be 0, 1, mod 4. Modular arithmetic. Who bet on that turning up? Well done. If you bet on modular arithmetic turning up. Of course modular arithmetic was going to turn up. Hooray. So let's put down a note here. Discriminant must be... I don't know if that's important, but I'm making a note of what's on each page. Okay. And maybe that's a reminder that I need to learn discriminant as well. Okay, where are we going? Sorry about the screen tearing. When I scroll, it's doing a kind of weird... Half the screen unloads, half of it loads. Timings. It's not Miro. Somebody spotted that it's not Miro. Almost reached the conclusion earlier. Yeah, we were thinking about that. Yeah, I don't think we were looking at the discriminant. We were close to thinking about mod 4 and mod 8 stuff. I guess we were just looking at one particular quadratic form. We hadn't noticed that for that one, I guess b is 0. So the discriminant is minus 8, which is 0 mod 4. Yeah. Squares. Yeah. Okay. There's some stuff down here about this thing being positive definite, negative definite, or indefinite. The definitions in here have nice bold writing in, which makes them easier to find. Okay, but I've already got one thing from this page, so let's look at the next page. Okay, it tells us how to identify if things are positive definite, negative definite, or indefinite. Is this what I want? There's a big proof here, different steps, and then a remark. So I want this. From now on, we should concentrate on positive definite binary quadratic forms. T finite is just infinite. Come on. Very good. D finite. I'm gonna positive definite. Now some of my notes are just a definition. Some of them are a kind of claim, and that's just going to be the word positive definite. So I remind myself that that's a thing. And also later if I want to find out where it is. I guess we're making a very detailed table of contents, but kind of personalised to what I'm picking out from each page. Oh my goodness, there's a theta and phi in here. What on earth's going on? We've got some Greek letters. Oh, is there some sort of proof what's going on? It's this root d. If d is positive, that might be an integer. Ugh. Theta is an expression for this, and phi. Those look like those are real numbers. Ooh. Okay. So something about being positive definite or not. We're going to look at positive definite binary quadratic forms. So I should need to decide if the one I was looking at was positive definite or not. I think it probably was. Let's have a quick look at the criteria up here. It's good to have one example, isn't it? X squared minus 2y squared maybe equaling 1, 2 or 3. No, not 3 we decided. We haven't decided whether it can actually take all of the other values or not. D is negative. D is negative, it's negative 8. And A is positive. Ah, good. F is positive definite. Good. Right. Okay, so we say something's reduced if either... I like the definitions. I think I'm currently in the mood for definitions. If I can take one definition from each page, I'll be happy. Either... Oh my goodness, look at this. That's hard to learn. So in this case, B can be 0. In that case, B can be 0 because even if A is 0, that would be included. Oh my goodness. The B could be 0 in either of these cases. And then we'd be looking at whether A is equal to C or not. No, if B is bigger than 0, we say it's reduced if either A and C are a larger number than B and equal to each other, or C still has to be larger than B. Okay. Some reduced definition. I'm going to try and copy it out into my notes. Are these notes or just a sort of list of things to learn about? Reduced. And that looks like this. B less than A, maybe less than or equal to A? Maybe less than or equal to A there. Let's have a quick check. I'm worried about the case where they're all equal. Does that count as reduced? Yes, it does. Good. Phew. Okay. So we've got different cases going on. Okay. Haven't yet got to any facts about whether or not these things take particular values or not. So looking out for those, I suppose. My win condition is we turn the page and it says something like, oh, positive definite forms take every value except 3s and 5s more 8s. They never do that, and they always take all other values. That'd be a win condition, because then I would have found the thing that I want to know, and I'd know that there are like n pages between me and that. Okay. Proof. I guess the punchline here is that reduced forms cannot be equivalent, by the way, but I'm not going to read that now. Okay, smallest integers represented by f are coprime x and y, or 0, both 0. What? I don't really care about the smallest integers they can take. Okay, this looks good. Every positive definite binary quadratic. I love things that start every. Every positive definite binary quadratic. So this is every, but then weakened a little bit by if it's positive definite. So not every binary quadratic form, but every positive definite binary quadratic form. That is a bit of word soup, isn't it? I guess you have to. That's why you take the notes. You've now seen enough to know that you read it positive definite in one breath, because we saw that definition a couple of pages ago, and binary quadratic form because we saw that definition several pages ago. So just by having that awareness of what was previously on the page, I now know that you're probably supposed to pronounce this. Every positive definite binary quadratic form is equivalent to a unique reduced form, or maybe unique pause, and then we saw reduced form as well. So the thing with maths, the definitions really matter, because then it sets the rules of the game for whatever's going to come next, and the thing that comes next tends to involve the definitions. Look, here they all are in a row. Right, an equivalent we saw as well, so if I've now underlined every word in that, right? Okay, positive definite binary form, positive definite. So I'm going to put positive definite implies equivalence to unique reduced form. And now this looks quite cohesive as well, right? So I can kind of see the point of learning about reduced and positive definite and equivalent, which did involve the discriminant, that you need to know. To understand this statement, you need to know this and that, and to understand this one, you need to know about discriminants. The whole thing's about binary quadratic forms, so everything kind of links. It's extremely connected. I mean, of course it is, but it's nice seeing that along the way. Right, this is page 24. On our speed run through, looking at what's in these notes, still haven't found values that you can take. I guess we could take the one that we've got, x squared minus 2y squared. That's got a larger than c, so it's not in reduced form. And I think it's probably equivalent to minus 2x squared plus y squared, probably. So that would be positive definite, and then I think that one is reduced because b is 0. No, wait, b is not less than a. I'm gonna have to think about whether or not that's reduced. Might get to reduce it to a unique. Might get to reduce it, and that would be an exciting thing to do, I suppose. I like the idea that the objects we're studying are complicated and need to be reduced down. If b equals 0, yes, okay. Right, yeah, no, okay. I am interested in b equals 0. That is interesting to me. But that's in the middle of a proof, so not getting in there now. Question: how many reduced forms are there with a given discriminant? Okay, so once you've decided what the discriminant is, equivalent to a unique reduced form. But they might not be equivalent to each other? No. Oh, there might be different reduced forms. Right. Just because you're equivalent to a unique reduced form doesn't mean that it's unique in the sense that each binary quadratic form is related to one reduced form. That particular reduced form is related to itself and unique. So they're not related to each other. We've got to count them. There might be many. Okay, and there's a proposition down here. There are finitely many reduced forms with discriminant d. Okay. You with me, chat? We've got a finitely many with finitely many. What are they? Finitely many reduced forms with discriminant d. So I think this is not quite. It's not quite true. It's losing me because it wasn't with me. We're just looking at what's there, but I feel like it's diverging from what I wanted. I was interested in the values of these, not really how many of them there are. It's always an ominous feeling when you're skimming through lecture notes, trying to find out what's going on in this course, right? Finitely many. There's a lot of counting here. Reduced form is quicker. Okay, there's not that many of them. Hey, look, class number. It's the number of reduced forms with discriminant d. Okay, we've proved it's finite, or we will have proved it's finite once we've read the proof. Proposition 35. Oh, was that proposition 35 gives ways to compute it? Just down here. Oh, so this proof that they're finitely many. Finding possibilities for A. Oh, so you sort of systematically work through the possibilities, right? Very roughly. If you know that b squared minus 4ac is a particular number, then b can't be. I guess b could be quite large. I should read the proof. Finitely many. There's a non-examinable section which mentions the generalized Riemann hypothesis, which looks fun. I think I've heard about this. So this is unproved, generalized Riemann hypothesis. Nobody knows. It's the sort of thing people sometimes assume because it seems likely to be true. And then once you've assumed it, from my vague understanding is that loads of interesting number theory stuff follows as a result. For example, the fact that h of d, the class number, can get really large as d tends towards negative infinity. And then I think I've heard about this, because it's funny or like a joke, right? That if it's false, somebody's done a separate proof that if it's false, then the same result. So putting that together, I think that means there's an amazing two-part proof, which starts part one. If GRH is true, then result follows. And then part two, if GRH is false, then it also follows. So either way, this is true, which is just a beautiful way around the not knowing whether GRH is true problem. I really like this. I think it's the thing I've heard about. This, I need to look this up. But how do you look up a kind of weird rumour that someone told you once? Ages ago, someone told me, oh, there's this thing mathematicians have proved where they've proved it true whether or not the Riemann hypothesis is true. Case 1, case 2. Really elegant. Okay, how am I going to source that? Is this the thing that my friend told me years ago? I'm going to have to get in touch with them again and find out. Right, okay. Non-examinable section. That's excellent stuff. Right, good. Somebody, if you're interested in that, because that sounds more interesting, that is the point of the non-examinable sections. The non-examinable sections are to demonstrate that there is additional material that might be more interesting. I think the thing you need to look up is the class number problem. I think that's the thing to search for. Okay, homework. Why am I taking, this is a stupid idea, I'm taking the non-examinable sort of hardest section of some Cambridge lecture notes and just being like, people watching at home, just go and learn that yourself, right? Just go and learn it. Learning is fun. Have I got a note from this page? I'm not sure I do. I'm on page 26. I'm not sure I've written anything down for page 26. X prime, Y prime, and co-prime if and only if X and Y are co-prime. That's the thing from before. Determinant 1. What is the point of this? I'm just going to write down F represents N if F takes the value N properly if it's co-prime. Oh, right, and then so check. Okay. So it properly represents. So I can go represents N. Properly represents N. Yes, cool. I've seen that as well. I like it a lot. It's a so it's a non-constructive proof. It's just off the top there, so I'll read the top line off. A similar thing to prove that there exist irrational numbers a and b, such that a to the b is rational. Because if root 2 to the root 2 is rational, then good, there you go, there's your example. It's probably not, but I don't know. But if it's irrational, hit that one to the power of root 2, and then you've got irrational to the irrational, but it's exactly equal to number 2. So good. Thinks that I might have mentioned it before, or somebody else might have mentioned it in chat. The sort of thing I like as an example of a non-constructive proof, where you end up knowing that there exists irrational numbers a and b such that a to the power of b is rational, but you do not know any examples for sure. You have this case, either my example is this or it's that, case 1, case 2, either way. So you end up knowing a fact is true without knowing any examples to back it up. So that's weird. There's usually someone in chat who says e to the I pi around now. If you're considering whether to count e to the I pi as an example of irrational number to the power of an irrational number being rational, then be my guest, but probably want to restrict to reals just to make it more interesting, I guess. Good, okay. We are skim reading some lecture notes. If you've just joined us, we're trying to zip through some lecture notes. We're trying to find out about whether x squared minus 2y squared can take particular values. And we've got a good lemma here, which says that n can be properly represented by a form f, which meant that n could be a value that f takes, if and only if f is equivalent to a form with first coefficient n. That seems like the fact that I should write down for this page. So, was that properly represents n if and only if f equivalent to form with a equals n. The first coefficient should be n. So if you can get it in the form of n something something, then right. So then it will definitely take the value because you can put in 1 and 0. And the other way round. Bazoo is in here! Hooray! Who called Bazoo? Somebody called Bazoo as being a thing that was likely to turn up. And there it is. Oh, that's crashed. Didn't even ask if I wanted to send a report. Turn it off and on again. Yes, I do want to connect. Oh, why would I not want to connect? Anyway. Why would I press the share button and then not? Anyway. Ooh, fun. I think I'm back. I was away briefly. Ah. Copium's being copium. I should get off the internet. Okay. Here's the idea of plugging in 1 and 0, because then it'll be ax squared will be a, and the other terms will be 0. It's back. Bazoo. Well done, people who claimed Bazoo. Oh, cursor. What's going on down here? NBC has appeared. Oh, because if we're equivalent to something with first coefficient n, then we're thinking about b squared minus 4nc. What happens if we know that there is a solution? What's going on here? So they're thinking about 1 on 1 in here. The quadratic form ABC. When are there BC such that NBC? Okay, so this question about can you take the value n becomes the question, can you write that in the form NBC? So it'd have to have the same discriminant. So b squared minus 4nc would have to be minus 3. So b squared would have to be minus 3 mod 4n. If there are solutions, then there are integers. So the NBC really is a form with that discriminant. But we don't know if they're equivalent. We know that NBC is equivalent. I'm now reading in a little bit more detail because this feels like we've got close to the thing I want to know. We know that NBC is equivalent to a reduced form of discriminant minus 3. But then this is some inequalities on what those reduced forms. There's only finitely many of them. So, the only reduced form discriminant. Okay, question. No, I hate that. I'm trying to join the dots from what are they down here. The only reduced form of discriminant minus 3 is this. So I think I want to repeat this calculation for minus 8 or something, right? At some point in my life, I'm going to repeat this calculation for minus 8. I'm going to say, aha. It gives me ideas about which values you can take by which things are equivalent. Every positive definite form is equivalent. Oh, they're all equivalent. Brilliant. So there is a form NBC looking like minus 1, minus 1, minus 1, equivalent to. So this tilde means equivalent to. If and only if there is a solution to w squared minus 3 mod 4n. So it's like the sort of thing I write down. Was that page 27? And now I'm on page 28. Do I want a note for page 28? Quick check. I am shopping for a note for page 28. I've only got 3 or 4 to go. Looking about 1 hour in. Okay, this is going to be theorem 38, I think, that I make a note of. I skipped. My eyes skimmed down to this example because examples, and look, I saw this x squared plus y squared. Oh, we're going to get there. We're going to get there. Sum of 2 squares. Sum of 2 squares. So good. Right. Okay. But let's make a note about theorem 38. N is properly represented. N is properly represented, not resented, properly represented by a form of discriminant D, by any form of discriminant D, then there is a solution to the congruence W squared is D mod 4n. We would say that D is a quadratic residue mod 4n. And then this way around, suppose there is a solution to the congruence this, then there is a form of discriminant D that properly represents it. I'm being very careful with these notes here to point out that it goes one way and not the other. What am I going to write down? I'm going to write down D quadratic residue mod 4. There's something about D quadratic residue mod 4n related to bunny quote marks because I'm being hand wavy because I don't understand the relationship, is n properly represented. Hey, there you go. I remembered that it was properly represented because I remembered that I had trouble saying it. By F with discriminant D. By some form of discriminant D. I think it's like that. Related to, I haven't decided if I mean implies or is implied by. So here, I guess I'm reading out this. Kevin, suppose there is a solution to this. Suppose that D is a quadratic residue mod 4n. Then there is a form of discriminant D. And there is a form of discriminant D. So my notes, there should be an arrow like this. N is probably just by some form of discriminant D. Okay, and I seem to have invented the shorthand disc for discriminant, unless that's already in the notes and I picked it up from the notes somewhere. But I was running out of space. Good. Okay. Time to read about sum of two squares. That proof looks nice and short, which, always good. Okay. So here's this form. And then this has got discriminant minus 4, because b squared is 0, minus 4ac is minus 4. And then the theorem just above us says, if n is properly represented by this, then there is a solution to this. Minus 4 would have to be a quadratic residue mod 4n. And then, if there is a solution to this, then it's properly represented by some form of discriminant minus 4. So then the sensible question is, what are the reduced forms of discriminant minus 4? If there's only one, then they're all equivalent. And this looks like this. Yep, once again, this is the only reduced form of discriminant minus 4. I don't know anything about the class number problem, but it looks like the world would be much easier if the number was always 1. The number of discriminants, if the number of reduced forms of a particular discriminant was always 1, then it looked like we wouldn't have to do this maths in particular. We would just say, well, there's only 1, it's unique, and then skip down to saying they're all equivalent. Even if there is a solution to w squared minus 4 mod 4, and this happens if and only if dividing by 4 somehow is v squared equivalent to minus 1 mod n. Aha! Now, n might be a composite number or prime number. We've already seen that if n's prime, this is the fact that we thought a little bit about n squared plus 1 a couple of weeks ago, and prime factors of n squared plus 1. They only come in one flavour. There might be some the two flavours of prime number are ones that are 1 more than a multiple of 4 and ones that are 1 less than a multiple of 4. And the prime factors of n squared plus 1, except for the number 2. Number 2, chill for now. Except that this might be an even number. The other prime factors, kind of non-2 prime factors of n squared plus 1, are always of the flavour 1 more than a multiple of 4, which I'm going to write as 1 mod 4 for shorthand. And there's something similar here that is minus 1. I care about this so much. Is minus 1 a square number mod n? Can you solve x squared is minus 1? mod n. I don't know the answer to this. I wish I did. But it's actually a couple of sections ago in these notes. There's some stuff about Jacobi symbols. Whether or not -1 is a square mod n. I know the answer for primes. For primes, the prime would have to be one more than multiple of 4. I don't know the answer for non-prime numbers. And then this is going to stop. So maybe we come back at some point. So the thing here, so let me read it again. This says if -1 is like exactly equivalent to asking, can your number be written as the sum of two squares? It's exactly the same as asking whether or not -1 is a quadratic residue mod n. That's so nice. I wouldn't guess that at all. Like, if x squared plus y squared equals n, then exists x tilde and y tilde such that x tilde plus y tilde plus 1 is a multiple of kn. Is a multiple k of n. That -1 is -1 is something squared mod n. Yeah, I wouldn't guess that at all. It looks a bit bazoo-tish actually, doesn't it? Bazoo. Anyway. Not now, getting too bogged down by I'm just a big sucker for whether or not there's a square root of -1 in your system. Let's do a very quick advert for that. In the mod 5 world, there is a square root of -1 because 2 squared is -1 mod 5. So 2 is kind of your square root of -1. In the mod 7 world, there's no square root of -1. Better example, mod 8 world, let's say, because in the mod 8 world we already saw that squares are 0 or 1 mod 8, never 7 mod 8. So there's nothing that squares to -1. In the mod 10 world, you've got things like 3 squared is -1 mod 10. So sometimes in some modular systems, some of these modular arithmetic systems, you get a square root of -1, and sometimes you don't. That is a recurring theme for me. We've seen the answer for prime numbers. So mod p is something like if p is 4k plus 1, then yes, there is a square root of -1, and if p is 4k minus 1, then no, there is not a square root of -1. But I don't understand the answer for numbers like 8 and 10, composite numbers. Maybe I should think about it a bit more. No, not right now. I think it comes from understanding Jacobi symbols, which are confusing to me. So something I've got to read more about. Right, do I have a note from page 28? I'm not sure I do. Oh, is this theorem up here? Yeah. Yeah, good. Okay, we're going to do a couple more, and then it'll be 3 o'clock. So over here, it's all going on in here. There's more examples. Oh, we've got Hensel's lemma. FB polynomial integer coefficients and PV and odd prime. Odd primes come up a lot in here. Non-2 primes. That's how you're supposed to say it, aren't you? That's what people say. A minute ago, I wrote non-2 on the board, and I should have written odd. Forgot that word. Suppose there's an x1 which is root mod p, and the derivative is non-zero. What? What? If we have a suitable solution mod p, we can bootstrap it to a solution mod p to the r. Is this what's on this page? This is what I'm going to write down? This is what I'm going to write down. Fairly general result, which will be helpful. Oof. This feels like a big bit of content, so I should write it down. I'm trying to memorize it so I can write it in my notes. Polynomial integer coefficients. Solution mod p, not repeated, or not. whatever that means. I can't say not repeated. Anyway. So what am I going to write here? F polynomial integer quantity coefficients. Spelling integer coefficients. Solution mod p. Solution mod p to the n, and there are some caveats on that I haven't written down, but I'll just remember that I haven't properly noted down what Hensel's lemma is. Should I put Hensel on the board? Maybe I should. Maybe this will be referred to later as Hensel. It's tricky because sometimes, until we've seen it, this might get used by name. Someone might say Hensel's lemma in 2 pages' time, or they might just have a polynomial and just do a thing without saying anything. Or they might say by proposition 39, so I kind of need to remember all of those, and maybe the slogan too. I am going to write down Hensel's lemma. Okay, next. A couple of pages. Oh, there's still more proof. The proof to this is long. Wait, what? And then it says long, and then it says the natural number n can be written as the sum of 2 coprime squares if and only if n is not divisible by 4 and all prime factors of n are congruent to 1 mod 4. What? What? I missed that. I missed the relevance of Hensel's lemma. Let's read the summary of the proof then. I really thought I was understanding as it was going through. There's the answer. Which things can be written as the sum of 2 coprime squares? Properly represented means coprime squares. Okay. And it's properly represented by 101 if and only if there's a solution to that, since that is the only reduced form. If and only if, because it's the only reduced form. If and only if there's a solution to this, let n be that. Then there is a solution to this if and only if there is a solution to, wait, this is exactly the thing I care about, whether or not -1 is a square root mod n. I didn't know this was coming up. Wait, what? So factorize n, look at all of these things. If and only if, using the Chinese remainder theorem to join together all of these things. So the primes, okay, it's got to be -1. I should have thought about it. -1 if and only if pi is 1 mod 4. Yep, that's the one we know. And there is that. This is the surprising one. Oh, it's a solution, right. I hadn't twigged, but v squared plus 1 is an example of a polynomial with integer coefficients. We're looking for solutions. Mod p to the n. If you have a solution, to this one, Hensel's lemma says that you get solutions mod p to the n for any power, which is brilliant. There is a solution to that if and only if there is a solution to this, and the solution to that one if and only if a1 is either 0 or 1. So the twos are separate; they do their own thing. What's that mean? Not a multiple of 4, just it's 2 to the ai up here. It says your number needs to be odd or a multiple of 2, but not a multiple of 4. Oh, here it is. The natural number n is the sum of 2 squares if and only if each prime congruent to 3 mod 4 occurring in the prime factorization of n occurs to an even power. Because if it didn't, if only it's the product of the square and a number that is the sum of 2 coprime squares. Yeah, I've got to think about that a bit, but that's not obvious to me the way the coprime thing works like this. And then amazing remarks, you can classify sums of 3 squares. Other proofs of Corollary 41 are available. Every natural number is the sum of 4 squares is a fantastic fact. if and only if each prime congruent to 3 mod 4 occurs to an even power. Okay, that's definitely what I'm writing down for this page. I think I missed a page in the excitement. N is sum of 2 squares if and only if each 3 mod 4 prime in N appears to an even power. And on the previous thing, it was about bit N being N is sum of 2 coprime squares if and only if, and then it's got to be, so there's restriction on the 2's, right? I didn't understand the 2's, the role of the number 2 on the way through here. Yeah, theorem 40. Sum of 2 coprime squares if and only if N is not divisible by 4. There it is. So is there a not divisible by 4 in here? No. You can multiply through it by a square. 4 is square, so you can multiply through it by 4. That's all right. All odd prime factors of N are congruent to 1 mod 4. All odd prime factors of N are congruent to 1 mod 4. Wow. Sum of 2 squares if it's made of just 1 mod 4 primes and maybe 1, 2. Okay, so the last few pages of these notes seem to be pretty focused on sum of 2 squares, which I didn't notice as we got close to it the first time round, right? In the kind of warm-up around page 27, 28. So around here, yeah, now it's talking about x squared plus xy plus y squared. But then here, yeah, it's introduced as an example, and I got excited and I looked down. I didn't really realise that this is like the main thing. Going on. I don't know, it's not obvious reading the lecture notes that that's going to be the main thing that we try to do for the rest of it, using the stuff along the way about counting these reduced forms and deciding that it's equivalent to whether or not -1. Equivalent to whether -1 is a quadratic residue mod N, which still makes me smile. Then we learn Hansel's lemma. Taylor series. Taylor series. Okay. So what do I want to do? I've got a choice here. I think. Taylor series. So going through and filling in the detail is really fun, because now we kind of know where we're going. We are interested in the case of x squared plus 1. That's right, we are. I'm also a little bit, I suppose, I'm interested in a bunch of quadratic forms now. So f prime is 2x. Cannot help us where p is 2, because this thing will always be 0. And we're looking for ones where the f prime is not. Okay, right, I think... so, ingredients in this big proof. I'm interested in this big proof. I might come back to x squared minus 2y squared. Yeah, I'm going to look at the big proof a little bit because it's here. Then I'm going to move back to x squared minus 2y squared and just try hitting it with some of the tools that I've seen. I don't really understand how to use the tools, but just try and muck in. And then that'll probably motivate me to go back and learn how to use the tools a bit more. I think I need a little bit more motivation before I go back and do the hard work. 2 is a very odd prime. Hey, Neutrino has redeemed Hydrate, which says everybody's got to drink some water. And I think it is a good moment to take a quick break. Nice sound. Yeah, I haven't worked it out. It's related to whether or not my sound's on, which terrifies me because it means... terrifies me. Okay, here's what I'm going to do. I'm going to leave the summary of the proof on the screen. Turn my camera and mic off for a second to grab a glass of water, you might like to grab a glass of water too, just to take in how brilliant prime numbers are. I'll be back in about 60 seconds. See ya. That was faster than I thought. Was I slower? I could have done an ad break. Feels bad doing an ad break when somebody's redeemed his channel points. It's like they've not real money, but it's like they've paid not real money to watch ads, which is not really what you're doing. Also, the ads are really loud. Just get Twitch to look at that. Right, okay. So, before the break, we were looking at this great fact. It's got these new words in for me, like properly represented. Something like coprime numbers, which I need to learn. And this being extremely related to whether or not -1 is a quadratic residue mod n. We factorise it, and let's say we're looking for this solution if and only if this if and only if I think is just the Chinese remainder theorem. It's kind of obvious one way around that if there's a solution mod n, then you can make a solution mod p. Just take exactly that value of v, and mod that thing. It all works out. And the way to combine them together is the Chinese remainder theorem. I guess the if part of this is the Chinese remainder theorem, and the only if is easy. And we know about these solutions from, gosh, all of the previous number theory that we've learnt on the stream a couple of weeks ago. So this is rather large to do the thing for primes. And then this is new. Might take a quick look at that. There is a solution. By the way, this answers my question, right? So if I look back down here, was it just down here? No, previous page. I had some notes, right? Oh yeah, this thing. Right, okay. So when I wrote this on the board, 15 minutes ago, I didn't know the answer, but now I've read the answer. It's in a couple of pages. It says that this has got too many 2's. But this is okay because 2 is acceptable, and 5 is good. So then the prediction is that if I look at something else that's made out of friendly primes, I'm going to call the 1 mod 4 ones friendly, I think. I need another example of a friendly prime, like 13. And so 13 is good. Let's put in a 5 squared or something. This is a bit daft. Why am I doing this? I think I wanted a larger example. I'm certainly getting one. 250 and 75 is 325. I'm losing all confidence. Welcome to the show. We're not exactly good at maths. We do our best. So the claim is there exists an n such that n squared is -1 mod 325. Anyone think of one? I think I can think of one. Oh, I suppose I'm supposed to do a Chinese remainder theorem, right? So mod 13, we would look to say, mod 13, it's 5 squared is minus 1 mod 13, and mod 25, I'm supposed to do some weird algebra. Wait, 18 squared is 324. Is that true? That's amazing. That's big if true. Is that really true? I used to know them all, up to 30 squared or something. That's one less than one of 325. Love it when that happens. That saves me from thinking, which is rather nice. What a great example. I'm astonished. Did we play this game? We played a game like this a couple of weeks ago, right? Where we tried to think of numbers that were... Yeah, we tried to play is there a square? Good. Okay, so we've got an answer now. We know when is there a number that squares to minus 1 mod n. Yes, this stuff about Jacobi symbols threw me, like caution, this is like, don't worry, answer in 3 pages. 1, 2, 3. Yeah, 2 pages really. 1, 2. Ha. Okay. A lot of hard work to get there though, because I kind of feel like we were along for the ride towards the end and at the start. The big bit in the middle about properly representing and counting the unique reduced forms. There's some hard work in there, which I might try and do a little bit of. Let's see if I can repeat any of this. So one of the reduced forms, this bit of the calculation looks quite concrete. Like you get stuck into this sort of thing. We want ABC such that this, and yeah, okay, I guess we do want this. This is what we want. Well, so the one I've got is like x squared minus 2y squared. So b squared minus 4ac. Oh, it's positive 8. I think I said negative 8 before. Is it positive definite? Let's skim back several pages. Because d is positive. Oh no, d is positive. No. F is indefinite. No. That's bad news. Does this mean I can't do anything with my x squared minus 2y squared? This course will only tell me about ones. No. My discriminant is positive? Ah. It'll only tell me about ones that look like ellipses, not hyperbolas. That's really sad. That's really sad. Can I fix it? Can I fix it? I can't fix it just by sticking a minus sign on there. That's wishful thinking. Doesn't change the d from positive to negative because it'll appear in b squared and it'll appear in a and c. Yeah, bother. Bother. Okay. it's going to be harder than I thought to investigate x squared minus 2y squared. That's really annoying. Yeah, because I'm now getting it. I'm getting a sense that everything after this is about positive definites, right? From now on, we should concentrate on positive definite binary quadratic forms. No! Come back, tell me about the negative, tell me about the indefinite ones. The relation on these, oh no. No, we're just biding our time. We'll learn this, then we'll learn more facts, and then we'll learn other things afterwards. And then eventually I'll understand x squared minus 2y squared. I'm just grumpy because it's I thought I'd nicely motivated this live stream by doing that example at the front, but now in hindsight I realised that I was not nicely motivating it. I was just doing something unrelated. And because I hadn't started yet, I didn't know it was unrelated to... Oh, that's really annoying. We did an experiment in trying to motivate what we were doing. I'm going to have to pick a new example to be interested in. Grim. choose a new hobby. Can I be interested in this one? How much do I care about this one? Not a lot. Not a lot. It's not the same, is it? I've actually exactly mistype it. Do I care about this one? A nice little ellipse. Care about it a bit, I suppose. I mean, not a lot. If we're asking, does it go to any integer points? Because I can see that it does. Okay, I need new motivation. How do you get new motivation when you're out of luck on your previous motivation? Hi, Super Snowman. I thought I knew what we were doing today. Then it turned out that the definition of the thing we were looking at slightly different from what I thought. We're looking at binary quadratic forms, which look like... See if I can summarise what's been going on. We're looking at binary quadratic forms which look like this, ax squared plus bxy plus cy squared, but the big one is x squared plus y squared, being the sum of two squares. We're interested in which numbers have that property, being the sum of two squares. And we followed through 10 pages of notes, we just skimmed through them to find out that numbers can be written as the sum of two coprime squares if they are not a multiple of 4, and if they're just made of primes that are 1 mod 4. But there's also the study extends to things with A's and B's and C's in there. Which is nice. I'm trying to work out if we got some interesting solutions to... But they're just not that interesting, right? Because they're bounded. They're bounded. The hyperbolas are the interesting ones. I think that's how the relationship works. I think we're looking at this b squared minus 4ac thing reminds me of the test for whether or not a quadratic is a parabola, ellipse, or a hyperbola. I can't talk about very large solutions to these things because I think they're bounded. Yeah, they're definitely bounded. So you're looking at, like, even if we put a reasonable number in here, it's a new idea for something to be interested in. We've got this like one big example, x squared plus y squared, which is in the course, in the lecture notes to great effect. I'm trying to think of a second one to be really interested in. My first guess of x squared minus 2y squared, which I talked about quite a bit at the start of this stream, turns out to be not the sort of binary quadratic form, not the right sort to be something we learn about in these lecture notes. So I'm trying to motivate myself to look at something different. Do I care about this one? See, I can't talk about very large solutions, right? Because clearly this can't be bigger than root n, and that can't be bigger than root n over 2. Annoying. I'm sorry, I brought you along for a ride and then turned out to go somewhere different. Which is also the story of what being hijacked is like, right? We were going to one place and then just went somewhere totally different, and we're going to live there now. Oh dear. Okay. Yeah, well, I didn't invent the disk abbreviation. It was in the notes. So disk, we'll put in the sad face, disk of 1, 0, minus 2 is 0 squared minus 1 minus. What's going on? Oh yeah, this way around. Yeah, okay. I lost all track of which way around things were for a second there. Because D's positive. The positive way around is bad news. Which is a shame, but that's where we are. Okay. Equivalent forms have the same discriminant, I believe that. We're skimming through the lecture notes again. I'm trying to decide what to read in detail. There are binary quadratic forms with the same discriminant that are not equivalent. Now, I don't know if these are in reduced form or not, but hey. Oh, I've thought of something I care about a little bit. So I also care about things like Pythagorean triples. Is this related to Pythagorean triples? Yeah, so Pythagorean triples says is yeah, okay. Pythagorean triples work like this. And we've seen that c squared, so to be the sum of two squares, which might or might not be coprime, needs to have. Wait, what? Oh, so no, wait. In this course, the answer would be yes, x equals c and y equals 0 is an example of a solution. That's not quite what I mean, is it? Looking for all possible solutions rather than just is there a solution? So that is harder as well. I think I'm going to have to follow through looking at x squared plus 2y squared. It's not the one that I wanted to look at. I think I'm going to follow through looking at that one. Here's x squared plus 6y squared. There's this notation ABC for the triple. This represents 1, but that one doesn't, but they have the same discriminant of 6. What's my discriminant now that I've changed this sign? It's now -8. Oh, did we look at discriminant -8 at some point? Well, let's follow through and look at the. Yep. So D is congruent to 0 mod 4. Good. It's -8. And yes, this is the thing we're talking about. Positive definite ones, which can never go negative, and yeah. So if you have A and C with different signs, then this can't be true. So C can't have different signs. They must both be positive. And more. So there is an and more. the A and C being positive so that you don't just plug in 0 and look at the ax squared term and say, if a is negative, I can make this whole thing negative. Okay. Similar as for quadratics in one variable. Okay, I don't really care about this proof. Equivalence relation, simple representation. Okay, so there's this method for simplifying them, I think, in grey here. There's some matrix multiplication going on, which simplifies these things down if you apply it. S looks like a reflection, right? It's going to switch C and A and change the sign of B. Oh my goodness. So if you start with a complicated relation, you can apply these transformations to find equivalent ones, which do. Oh my goodness, look at this. A keeps A the same. No, what? Simplifies them down. So I want to know whether, so x squared plus 2y squared is reduced because b is 0, which is less than or equal to 1, which is less than 2. Good. B is less than or equal to A is less than C. A and C, okay, so A and C have to be positive numbers in order for it to be positive definite. So minus A has to be less than A. It's another way of saying that. A weird way of saying it, but another way of saying it. They might be equal, in which case fine, just make sure B is somewhere in between. Okay. So I want to see if there are any others. Others with discriminant minus 8. They would have b squared minus 4ac is b squared minus 4ac equals minus 8 with b less than or equal to, so a mod b less than or equal to a less than or equal to c. Oops. I can't really see how to make progress with that, so I'm going to come back to it. So reduced forms are not equivalent, and then counting them is over here. How many are there? D is minus 24. Okay, right, so let's look at this method in here then. Let D be a fixed negative integer. Minus 8 for me, please. There are finitely many reduced forms. We're looking for this. B squared minus 4ac is equal to minus 8. And mod b less than or equal to a less than or equal to c. Then d is equal to b squared minus 4ac is less than or equal to ac, because b mod b is less than a is less than c, minus 3a squared. Okay. Where's that? Yeah, okay. So negative, but not very. So a squared minus 8 is less than or equal to minus 3a squared. So a squared is less than or equal to 8 over 3. 8 over 3 is not as big as 4, is it, at all? So a is 1. Finitely many possibilities for a. Mod b is less than a. So you've got b equals 0 or b equals 1. Finitely many possibilities for b. And then c, we need the right discriminant. So in here we get c equals 2, which is the one we had before. And over here we have b squared minus 4ac is equal to minus 8. But that's not going to give us an integer. That's going to give us c is 9 over 4, which doesn't work. So it's determined by a, b, and d. So this is, so for minus 8, just 1. Good, okay. So this means if we're looking for solutions to x squared plus 2y squared equals n, that's something to do with and if we see somewhere a reduced form with the discriminant d, we know that it's this one. Makes me wonder a little bit more about the class number problem actually, which I'm going to Google now. Earlier in the stream, I instructed you to Google the class number problem, and now look, I've looked up the Wikipedia page too. Do I want the Wikipedia page or do I want the MathWorld page? I think I want both. MathWorld is sometimes better just for being shorter. Complete list of fundamental binary quadratic form discriminants. So that's the class number is given by, yep. Sometimes some people put this minus sign in. Solution for m equals 1. Number of gaps. Essentially correct. 952, wait, but isn't that... Oh no, this is the other way around, right? Find me those number d. Find me those number d such that the answer is 1. I like those. We just saw that d equals 8 is an example. Wait, what? The 9 values? There are only 9 values? What? Well, the 9 values of n of minus d having h of minus d equals 1, where minus d is the binary corresponding quadratic field. What an quadratic field? The Heegner numbers, and there are 9 of them, and they look cool. The Heegner numbers have a number of fascinating properties. Well, rabbit hole, because any sequence that goes 1, 2, 3, 7, 11, 19, 43, 67, and 163 has my attention. Only 9 such numbers exist. Both proofs were accepted. This page is doing a lot of not completely accepted. Then solve m equals 2, 3, 4, 5, 6, 7, odd m up to 23. Watkins 2004 has solved it for all m up to hundreds. It's pretty good. So the answer is not just always 1. This makes me feel like the answer is never 1, including not my case, right? N of minus d. N of minus d. It's n of minus d. Oh no. Oh no. Oh no. Binary quadratic forms its class numbers equal to 1. Except for these ones which correspond to those, including the one we just looked at. This is class number problem. There are only 9 Heegner numbers. 1, minus 2, 3, 7, 11, 19, 43, and 67, 163. Discriminants. Oh, sorry, right, okay. These are the numbers corresponding to discriminants, and we saw this one. Corresponding to discriminant minus 8. That one corresponds to discriminant minus... The first ones have some extra factors of 4 going on, which is alluded to up here. Anyway, I'm getting lost in the essentially correct. That's essentially correct again. They also explain why Euler's prime generating polynomial is surprisingly good at producing primes. Okay, one more. We're going to rabbit hole one more link to the J function because it's got the same first letter as me. Oh yes, it's a modular function with the number 1728 in it. What? What on earth is this? 1728 is 12 cubed. Gauss was aware. What? And related to the factors of the group order the Motz group. This is definitely some maths. Oh, I love maths. What is this? I swear, Wolfram MathWorld is brilliant for just some pages looking like this, just being like, here's some chat, and some pages being like, here's all the equations that exist on this topic. There are some special points mapped in. This is definitely some maths. Look, here's some Right, I've heard of this. E to the pi. I wanted to scroll down until I found this. An almost integer. E to the pi root 163 is very close to being an integer because of deep maths, which is brill. The initial term because of the Laurent expansion or something. It's amazing stuff. When I was at university, there was an essay. When did we write the essays? The sort of essay competition, essay prize thing where you chose a topic from a list and you wrote about that topic. When was this? Sort of second year, third year? Might have been fourth year essay. I can't remember if it was a college essay prize for this particular topic or for the dissertation sort of thing. Anyway, there was a list of projects, and I was heavily into applied maths at the time, so I was mostly looking at those ones, of course. But they're all in the same dog, so you scroll through and you see that some of the people doing number theory have the option to do a project, doing some reading and maybe digging deeper into just root 163. That's the thing things they were looking into. I think that was a project set by Ben Green. Let's see if I can find their source for that. Yeah, it's probably this sort of thing. So Ben Green's got something on Ben Green's website, which starts off introduction, e to the pi root 163, very close. Use this approximation of pi, and then some of this maths. Introduction of elliptic curves. This is like an all-star group of everything, isn't it? Right, good. Okay, we went one too deep into the rabbit hole. Wikipedia instead. I think I just want to know the answer to the class number problem, right? Class number 1. Not very many. 1934, prove the Gauss conjecture. Good. Only finitely many. Okay. But then this sequence has got loads of ones in, so I think this is counting something different. I think I don't understand the link to quadratic fields. Maybe I should. Contrasting case of real quadratic fields, much less is known. Okay, right, good. We're not going to read this now. They predict about 75.54. What? No, I can't resist reading this stuff. It's too good. For real fields, they predict that about 3/4 of the fields obtained by joining the square root of a prime will have class number 1. Okay, amazing. Great stuff. About 3/4. Actually, about 75.45%. Classic maths answer. Right, we're not going to understand the class number problem, are we? But it seemed like the punchline there was that this is unlikely to be unique. I can imagine really stupid questions then, like what are the reduced forms? So apparently there's a reduced form with discriminant minus 163. So that's kind of cool. Can I find that? Apparently this is unique. Where, once again, we want mod B less than equal to A less than or equal to C. Apparently this has got a unique solution, which feels like a thing that, 163 is not that large. Maybe I should be able to check this. So the proof or the counter, the strategy works like this. Mod B is not that big, so this is not as big as not as big as a squared minus 4ac, and minus 4ac, that would be larger if you wrote minus 4aa, because I'd be replacing this negative thing with a smaller, less negative thing, which is only minus 3a squared. Okay, so I've got to divide this, but then a squared could be, well, it's got to be positive, so 1, I've got to write down the squares up to, this is slightly larger than 50, isn't it? I'm so bad at division. Squares up to about 54? Doesn't matter, does it? 1, 4, 9, 16, 25, 36, 49. So then I'm looking at my values of A, and in each case there's only finitely many values of B. So let's try and find some of them. So if A equals 1, then B could be 0. Oh, excuse me. B could be 0 or B could be 1. If B is 0, then we need minus 4ac to be 163, which is ridiculous. If B is 1, then we need minus 4ac to be minus 160. I want to say 4. Is it 4? Yeah, which is looking quite good. Yes, it's 41. Oh, I accidentally feel like I understand a thing. We discover this quadratic form. B is 1. B squared minus 4ac. 1 minus 1 squared minus 4 times a times c. 4 times a times 41, which is then 1 take away 164, which is minus 163. I really didn't think I was going to find any, let alone that it would involve a number that I've seen. I've seen a number 41, right? So it's just the... So there's something going on with this, which does look a bit like that quadratic x squared plus x plus 41, right? What's going on there? Time to have a look at that one. I've discovered a new binary quadratic form that I care about a bit. I should go through and check the other cases, right? So there's 2, 3, 4, 5, 6, 7. And then each case has got progressively more and more possibilities for what B could be. Because, ooh, B could be negative. No, that's all right, isn't it? You can always flip B. Always flip the sign of B and get a different reduced form. What's going on there? Oh, maybe B. Maybe you have to take the positive one for your reduced form anyway. Was there anything about flipping B? No. So if this is reduced and I flip the sign of B, surely that shouldn't matter, right? Wherever A was able to see that, now I don't have a reduced form, because it won't be true this is the case. And if A is less than C, B is going to be somewhere inside this region, so minus B is as well. So it feels like we're opening the door to things not being unique if B is non-zero. Why do I not find this? What about x squared minus xy plus 41y squared? That's also got b squared minus 4ac is minus 163. Somehow this doesn't count. So this is a good exercise if you're trying to understand something, is to try and find things you don't understand, things you do understand, or thought you did. It's different. Okay, let's symmetrize that. You're supposed to find things you think you understand and things you think you don't understand that contradict each other, or appear to maybe that wouldn't really make sense if these things contradict each other. you suspect they contradict. Because then you're wrong about something. You're either wrong about whether you understood the thing in the first place, or you're wrong about whether you don't understand it. Maybe you do. Or maybe you're wrong that they contradict each other. Those are the three ways you might be wrong. I'm going to try and discover which way around I'm wrong. Because I think there's a unique reduced form with discriminant minus 163. On the other hand, I think I found two. So, what? Maybe they don't count. I'm wrong about the definition. Maybe my calculation is wrong, and I had found the unique one, and then wrote down a second one for no reason. Or maybe they don't contradict in some other way. I'm trying to work out here. So my value of A was 1. Oh, so this is subtle. This is subtle. So then I wanted to put in B as plus or minus 1. But if I put in minus 1, there's no equality here. Huh. So you can't flip the sign of B if it was actually equal to A. If B, A, and C are all different numbers, then you can just flip the sign of B and you'll get a different quadratic, a different reduced binary quadratic form. If A, B, and C are all different. But this one, because this one's got B equals minus A, so it's not allowed. Okay, so the calculation was wrong because I didn't understand the definition, but the reason I wrote down that bit of calculation was because I've misunderstood. The things go together. Apparently this is unique. I should go and check the rest, but I want to wrap up by looking at the quadratic form in decimals, which is 1, 1, 41. It's a weird one. It's a weird one. Oh, I want to look at different values that it might take. Does it take the value 41? Yes, it does. It takes that at... delete a couple of these. Takes that at the value 0, 1. Right here. So something I can do, I suppose, is to look at this for different values of n. Instead of just looking at the value n is 41, I can look at the contours to look at this for the values of when is this 1, when is it 2, when is it 3, when is it 4, and so on, up to like 100 or something. And my computer whirs a lot and draws this sort of thing. And I suppose, don't show me the minor grid lines. Stop it. That's a lot of lines. It's not very happy about this. Too much. Some of these go through integer points and some of them don't. I'm thinking a little bit about the relationship between the sequence n squared plus n plus 41, which I can kind of see in the coefficients, right, along the line y equals 1. So along here, apparently this sequence is good at generating primes. Good at generating primes. Good at generating primes because some sort of deep fact about the divisibility. So that over here, what? The sequence, okay, so the sequence goes, you have to go up to 43 to find the next point where it takes that value. At which point the value of ax squared plus bxy plus cy squared is 43, right? Yeah, what's going on? Why are my values so small? Why are they all bunching up like that? Quadratics, eh? Yes, I want to think about the sequence, but the sequence marches off to the right really quickly. Things don't go through any integer points for ages. I thought this picture would look better than it does, if I'm honest. It's slightly slanted. I don't know if you can see that. Because of the B term. There's a slight tilt to it. This bit is slightly above the axis, and this bit is slightly below the axis. Slight tilt to it. Bit much. That's really, my computer is not happy with that much Desmos all at once. But I don't want to skip numbers as well, right? See, that worked. Because that generated, so I'm thinking about plugging in numbers x. So I'm thinking about generating numbers like n squared plus n plus 41, which I'm imagining doing by setting x equal to integers n and y equal to 1. So as I do that, when I put in 0, I get 41. I don't, right? X is 0. Wait, so if I put in 41 over here, that one goes through this integer point. That's a good start. And then when I put in n is 2, I get 4 plus 2 plus 41 is 47. Okay, so that goes through this point over here. So that's progress. Okay, so if I look at all of these, but then the points where they intersect with not just the red line, but at integer x coordinates. Oh, I don't know. Too many variables all at once. Some deep lore about whether or not this thing has factors, which we saw when we looked at x squared plus y squared. It came down to things being, looking at the primes mod, looking at the factorization and having some restrictions on the prime factorization. So I can imagine that the numbers you get out of this, the restriction is loads of restrictions, but it only satisfies when you get out to right. But integer solutions is not the same thing as a composite value of n squared plus n plus 41. So I'm jumping around too much between topics. I've been really distracted by the cool bit of the course, looking for unique things. Okay, just to try and tidy this up, instead of thinking about the representations again, or whether things are linked together. Yep. And then, right, so in here, coming down to quadratic residues. Instead of that, I'm going to sneakily take just 2 minutes here to look at the problem sheet to see what people are being given questions about. And the questions usually go variety of straightforward and impossible. Are forms like this equivalent? There you go, so check that you know what equivalent means. We should check the discriminant of these things as a first start, and then we try and look for things and then decide. Maybe we'll reduce them to do that flippy switchy stuff to reduce them down to basic forms. Okay, prove that that's an equivalence relation. That seems all right because SL2Z, you've got inverses. Make a list of all reduced positive definite quadratic forms of discriminant D. And 163 is on the list. So completing that calculation for 163 is on the question sheet. Find the smallest positive integer that can be represented by this one. That was mentioned in the notes. We didn't note it, but get this into its reduced form. And then look at A, C. A is the smallest thing that you can make. Necessary and sufficient condition for prime P to be represented by the form of x squared plus 3y squared. That sounds fun. That does look fun. Is that reduced form? Yeah. B is 0, A is 1, C is 3. Looks fine. Is there a positive definite binary quadratic form that represents 2 and the primes congruent to 1 mod 8 or 3 mod 8 but no other primes? That's fun. So to represent 2, it's going to have quite a small coefficient there, right? What's going to be equivalent to some reduced form? Oh, we're looking for it. Okay, no other primes. That's brilliant. And then 12, find a necessary and sufficient condition for a positive. Oh, it's the last question on the sheet as well. Properly represented by at least one of the two forms. Whoa. Did you do them separately? I hope. Assume that n is coprime to 15 and properly represented by at least one of the forms. Coprime to 15. So the congruence conditions modulo 15 allow one to decide which form represents n. Oh no. At least one of the forms. Looking mod 15 is enough. Oh, okay, brilliant stuff. Check the next sheet just in case there's some spillover. No, now it's onto prime number stuff. Mobius function. Ugh. Okay, so not that many questions on the sheet about quadratic forms. This is what Cambridge students were given to think about all of the stuff we've seen, but they've spent about 5 lectures on it, which is, gosh, about 2 and a bit weeks. We've spent 2 and a tiny bit hours. I think we could have a stab at some of these if we had to, but if we were at university, or if we were studying this more than on Sunday afternoons, we would obviously go back and practice a lot more and make sure we understood things a lot more before we attempted any of these. I feel like I could do 8 and 6. 8 and 6, but maybe not the fast way. 8 and 6 with some work. Okay. At 4 o'clock, I think I'm going to wrap up. Neutrino wins a prize for, and that for remembering the number 75.45%. We should do more deep dives on MathWorld. If you like a stream of me just looking at maths on the internet, going, oh, then that's a good example of what the research process is like for Oxford Online Maths Club, and also I don't think I'd learn very much. See you all next week. I think where's next week? Probably see you next week. The 18th? Yeah. We'll find out. I'll put something in the Discord if I'm not around next week. I don't miss very many Sundays, turns out. Take care, everyone. Have a nice rest of the weekend. See some of you around middle of the week for Oxford Online Maths Club, and maybe see some of you next Sunday. Bye.